I will start with the research aim. So the idea was to continue on the previous research where we conducted the research whether and how CRDTs or commutative replicated data types are useful for in geospatial domain in general, let's say. But during that research, we didn't investigate how everything behaves when large geometries with a lot of vertices are coedited. So in this research, we wanted to investigate that part. So I will give a very short background introduction because the time is short. Then a few words about the test setup, how we did the testing, and some results. So CRDTs, it's a technology that decomposes the content which is being co-edited and stores it into some data structure where each item is assigned identifier, and those identifiers are then used to do remote insertions. A little bit differently than operational transformation. So two important concepts are CRDT model and view, and often a lot of conversion between the two has to be done. So the life cycle of an operation starts upstream or on the local client, and then goes downstream to the remote client. And here we can see some things that happen in the meantime. So those yellow parts are kind of performance hotspots, which need to be handled carefully when performance is important. A few words about the test setup. So we had the application from the previous research, which was implemented with OpenLayers and this small CRDT library, which is complete and correct. And we had this concept of tentative operations, which we used in this research. So we did some small performance enhancement and primarily on this find by ID part of the system. So the architecture is a little bit changed because in the original architecture, all the incoming remote operations are executed and drawn immediately. Where in this setup, we changed it to keep the performance because a lot of incoming operations were expected to come from all the other remote clients. So the architecture is a little bit modified. So all the incoming operations are stopped and executed and redrawn after the local operation is done. So regarding the test setup, we used two not very high performance, let's say, hardware setups. We didn't want to to go with the best available stuff because it can be expected that not everybody will have such hardware available. So you see two AMD CPUs, 2 and 4 generations old. And for the data, we created test geometries or test polygons by using some Corinne polygons of 1, 2, and 300,000 points. And we just added a small polygon on the end of each of those polygons where the load on the algorithms will be highest. So in this particular case, the outer boundary goes clockwise, which is irrelevant for the technology itself. So how we did the testing? We had a single user which did all the test runs, and we also implemented some automatic clients to be able to simulate increased load with many incoming remote operations on the local test client. So you see that we went from 15 to 60 remote clients, and we did the testing in two phases, where the user was first editing in one direction and from the same point on the other direction in all test sessions. So a few words about the test results. You see some statistics here. So almost 4,000 remote operations were generated in each session by those automatic clients, and this range index misses were about 1/5. So this is the situation where this speed up technique couldn't speed up this one of those critical critical parts or algorithms. So first on the CRDT integration, where the operation is actually integrated in the data structure, so which heavily depends on the find by identifier algorithm, and which uses this speed up technique, which can hit and miss, doesn't hit every time. So the operations which were indexed, so which were able to use the speed up technique, were in both parts. So in local integration and in remote integration were below 1 millisecond. And those which were not able to use the speed up technique were from 1 to 3.5 milliseconds for the worst case. So this is low-end platform with 300,000 points polygon. So that's pretty good. Upstream GUI coupling. So one of those model to view transformations is implemented just with the simple loop counting the tombstones from the left of the position where the element is to be integrated. So this is also pretty good. So you see that 300,000 K polygon with the low-end platform was up to 2.5 milliseconds. So kind of the first part, let's say not so good part, was this model to view transformation. You see the numbers, and it's integrated simply using a JavaScript array filter, which most likely can be made faster. So this is just a simplest implementation. So that's 12 milliseconds in the worst part. So on the downstream, so remote operations which are coming to the local client, you see that they were so on the right part you can see the number of operations per burst. So you see that those this number was coming to 120 operations which were accumulated before local integration was done. And on the high-end platform, it's about 70 milliseconds in the worst case for those 120, so a little bit around half a millisecond per operation. So there are different types of operation: inserts, deletes, updates, indexed, unindexed. And this spike that's seen in the middle is part where the user was changing from phase 1 to phase 2. So he had to scroll and move around. So many more operations were accumulated and had to be executed at once. So then we calculated 19th percentile of those times, and we can see that everything except for this weaker platform on 300K polygon was able to be done in almost, let's say, below 50 milliseconds. On the GUI part, so how fast was OpenLayers able to do the rendering, the redrawing of the geometry? We see that currently the system works that the feature has to be selected, and then the load on the OpenLayers is higher. In that case, it took hundreds of milliseconds, up to 1 second in the worst case. But when the feature is not selected, then this kind of approach also can be used. It's in tens of milliseconds, so this is also, let's say not bad. Coming to the recap, so to have some reference frame to be able to say, okay, it's okay or not okay, we use this paper which concluded that this 100 millisecond is let's say unacceptable, still unacceptable latency on the GUI, which will not hinder user experience of the system too much. And coming from that, so to have a little recap. So we see that CRDT integration, so the actual CRDT insertion algorithm, which uses this find by identifier algorithm, was up to 6 milliseconds, so that we can consider that is pretty good. Sorry. OpenLayers provides the position in the view, so this doesn't have to be calculated by some additional algorithm, so it can be used from OpenLayers direct segments. If it wasn't so, then something would need to be implemented to also do this part. So on the upstream, on the local part, when local client is preparing and creating his operation, on the low-end platform with 300K polygon, this snapping was starting to be a little bit laggy. So more or less, we can say that it depends on the GUI how fast it will work for the user experience to still be kept. On the downstream part, so in the part where the client is receiving and executing other clients' operations. So again, even those remote operations that had to be executed without using those speed up techniques were still in the range of several milliseconds. And the weakest part is this model to view transformation, which is implemented very simply with the array filter. So this most likely can also be done faster. And in the worst case, OpenLayers was able to do the redraw in well under 50 milliseconds. So we are well below this 100 milliseconds acceptable limit, let's say. And coming to conclusions, in the original PowerPoint presentation, this right part was hidden, so it was supposed to appear later. But here, okay, we see that we can say that upstream performance, so what local client is doing with the operations which are generated on the local client, the performance is very, very good. This position in view is taken by OpenLayers, so OpenLayers provides that part for the whole setup. And also both this approach where all the remote operations are accumulated and executed and rendered in bursts can be used, but also judging on the times, it can be done that even everything can be done in real time. So all the remote operations are executed and probably also redrawn on the GUI. So the conclusion is that CRDTs and OpenLayers can be used even for real-time co-editing of even of high vertex count geometries on not some very special hardware and with a relatively high load where 60 simultaneous users are working on the same geometry. So a lot has to be done, not only by what the local user is doing, but also all the remote operations which are incoming from the other users. And that's more or less it.